Now there's one more thing we have to talk about and then we can call it a day. And we're going to introduce you to the half-life. And that's kind of a good name, I would say, for what this is. This is the time it takes for half of the reactant to be used up, or if you like, half of the product to be made. And so we can look at this equation here, and we can go ahead and we can say, well, at the start of the experiment, okay, we know the original concentration, and we know that time equals 0. And at the half-life, okay, what do we know? Well, we know the concentration at time equal to the half-life is 1/2 of the original concentration. So what that means is that we can look at this expression here and we can substitute in for these three values and we can solve for the half-life. So let's go ahead and push up and give us some room here. So what do we have? We've got the log at the concentration at some time. So let's make this be the half-life over the concentration at the start of the experiment is equal to minus k times by the half-life. We know that the concentration at the half-life is 1/2 of the original value. We're dividing that by the original value still, and that's equal to minus k times t sub 1/2, the half-life. Now, if you look at the log term, whatever your initial concentration is, you can see it doesn't actually matter. And that's one really neat thing about the half-life for a first-order reaction. It doesn't matter what the concentration starts out at. It's independent. So we can go ahead now and we can say, well, this is just the log of 1/2, and that's equal to minus k times by the half-life. And so the half-life itself is the log of 1/2 over minus k. Now you can either just go ahead and calculate this, or if you're comfortable, you can say, well, 1/2 is the logarithm of 1 divided by 2, which is the log of 1 minus the log of 2, and that's minus log 2. And then you got the minus on the top and the bottom, giving you the natural logarithm of 2 over k. A lot of people like to go one step further, and if we go ahead and we actually substitute in for the logarithm of 2, the natural logarithm, to 3 significant figures, it's 0.693, and so we're dividing that by k. And that's one of those numbers that comes up over and over in science. And so whenever you see 0.693, you should think someone at some place took the natural logarithm of 2. So again, just to reiterate here, so the half-life, so for a first order reaction, T sub 1/2, the half-life, does not depend on the original concentration. And that is really, really important. So that means for any chemical reaction or nuclear reaction, the amount of material you've got doesn't affect the rate it takes for half of it to react away. Let's have a quick look at a figure of a first order reaction as time goes by. So this is a figure from our textbook actually, and you can see that on the y-axis you're basically plotting the concentration, and the x-axis you're plotting the time. And you can see here there's a whole bunch of balls, 16, right? And then at the original concentration, right, there's 16 balls per cube. And then when the concentration halves to 8, the amount of time it takes is the half-life, T sub 1/2. Now you've got 8 and you want to half that to 4, then you've got to wait the same amount of time, and now you've got 1/2 of what you had before, 1/4 of what you started with. And again, every time you wait a half-life, you get half of what's left. So you can see after one half-life, you've got half of what you started with. After another half-life, you've got half of 1/2. That's 1/4. After a third half-life, you've got 1/2 of 1/2 of 1/2, which is 1 1/8. So after 1 half-life, you got this. 2 half-lives, you got 1/4. 3 half-lives, you've got 1/8, and so on. Now, if we go back to carbon-14, and so carbon-14, we said has a rate constant K of 3.83 times 10 to the minus 12 per second. And so we can calculate its half-life by basically taking the log of 2.693 and dividing it by that value of K. And when you do that, you get an enormous number in seconds. And we probably don't like to think about 1.8 times 10 to the 11 seconds, but if you convert to years, 5,730 years. And so what that means is that approximately every 6,000 years, half of these atoms decay. And so after 12,000 years, you've got only 1/4 left. 18,000 years, you've got 1/8, and so on. A lot of people say very approximately, so sort of a rule of thumb is that after 8 half-lives, you've almost got none of your original sample left. For instance, if you go ahead and you go have sort of radioactive iodine treatment, I believe the radioactive iodine has got a half-life of about a week. So what that means is that after about 8 weeks, it's almost all gone from your body, which means if you go through the airport, you won't set off the radiation detectors. It also means, and I'm not a lawyer, so don't quote me on this, that after 8 half-lives have passed, you can actually throw this radioactive material in the garbage can. Pretty neat.